Hey y'all, what's up? This is Coach Hyde. Drinking some H2O, bringing you some Hyde science. Um, Talking about Newton's laws. Now, the other video we talked about Newton's first law of inertia, which you see here. An object at rest tends to stay at rest. An object in motion tends to stay in motion, unless acted on by outside force. Now, I don't really like this. Oops, hang on. Trying to figure out how to use my pen. Let's try that. Oh yeah, cooking with gas now. Now this part of the law. Today we're going into Newton's second law. Newton's second law is force equals mass times acceleration, right? So this part on this first law here, right? The reason why I say I don't like this part down here is because Newton's first law is just specifically talking about objects that are moving have inertia, which means that they have a tendency to continue to move. Objects that are sitting still, they're at rest, they have inertia, they tend to stay at rest. And that's just the way it is. Now if we're talking about changing that inertia, all right, we want to make it move if it's not moving, or we want to make it stop if it is stopping, or if it is moving. Then we start talking about this force here. And this force, this unbalanced force is talking about, well, that's Newton's second law. So let's look down here. I'm going to go and find it real quick. All right, so Newton's second law. Newton's second law is, we already talked about it, right? Already said it. Force equals mass times acceleration. So any force, right? Any force, any push that you can find, that you can see, that you know where it's at. You saw it the other day. It was a push. That was a force. Also, any pull. Any push or pull you see, no matter what, is a force. All right, so we are pushing down on the earth. We have weight. Weight is a force. If you punch somebody in the face, that is a push. That is a force. Right? If you tackle somebody in football and you pull them to the ground, that is a force. Right? Any push, any pull, no matter how big, no matter how small, is a force. And that's what Newton's second law is. And it's just saying for any force, if you know the mass and you know the acceleration, you can calculate the force. Or calculate something else. If you know two of those three things, you can figure out the other one, right? But we specifically talk about the force a little bit. Something interesting I want to bring up. We talked about weight several weeks back. Weight and force, they're just the same thing. So I'm gonna try this color right here. If we're looking at this formula here, force equals mass times acceleration, and we look at this formula here, weight equals mass times gravity, they are the exact same thing. They don't look the same. They are the exact same thing. All right, so what do I mean by that? Follow me here. So if force equals mass times acceleration is Newton's second law, and weight equals mass times gravity. All right, think this through now. Isn't weight a force? Well, weight is you pushing down the earth. Yes, weight is a force. So if I'm solving for weight, I can very well be solving for force, or vice versa. Do you use mass to calculate for weight? Yeah. Weight is the measurement of the force of your mass. And then about this acceleration. Well, when you talk about weight, you usually use gravity of where you're at. Hey, that is an acceleration. So literally the same thing. Right? You solve them the same, they look the same, they work the same. You got a couple different letters of the alphabet in there, but they the same. All right, so moving on. Newton's second law is not all mathematical. Some of it's conceptual. So, for example, here we have, let me get my little clicker thing ready real quick. All right, we got a big rock. Okay, the big rock has a weight of 5 newtons, and we got a small rock. Small rock has a weight of 0.5 newtons. So, based on this relationship, we can figure out several different things. So, that big rock right here, right, this big rock is 10 times bigger than this rock. Right? Well, using Newton's laws, we know that mass and acceleration are tied together. right? If you have a big mass, you got a small acceleration. If you have a big acceleration, you have a small mass. So if we want to accelerate them at the same rate, right? Right. If I want them to be equal, I will need 10 times the force for this big rock to accelerate the same as a small rock, or kind of, you know, however you want to look at it as you go. So continuing on, do or do nots. You can't see that part up here. Do or do not. Do or do not. There's only, or there's a try. Sorry, I forgot. Brain fart. My bad. Anyway, they were fighting and stuff here in a meme. It won't work with the way I got the PowerPoint situation. This was a meme here of Luke with the rock moving and all that. What I ask is how do you know there's forces here? It's not the Star Wars invisible force when nothing happens. Push or pull means force. Moving on up. Moving on up. This one here, we got some different balls of different sizes. All right, so what I wanted to take a look at, to think about a little bit here. I want something like bright green. That'll work. See if this worked. That didn't work. Sorry, I probably should figure this out other times. All right, so what we got a baseball that is the lightest, football is medium, and a brick is the biggest. Now, just kind of same thing. If you want all of these to accelerate the most, right, you're going to have to apply the largest force to this one. So 8 Newton brick is 4 times heavier than the baseball. So you would need 4 times the force to accelerate the baseball the same way. The football is twice as big as the baseball, so we need 2 times the force to accelerate the football at the same speed. So something to kind of to think about, right? If you apply the same force to objects, so let's say we applied a 12 Newton force to these, to the we'll say the football and the baseball. We saw out a 12 Newton force to both of these. Well, F equals ma. Sorry, my little screen got in the way. So we got mass. If we multiply the mass times the acceleration, that's equal 12. Well, if the baseball, right, has a mass of 2, and football has a mass of 4, I know that's a weight, but whatever. This one is the smaller one. Okay, this is the bigger one. So we'll say this is a bigger one. This is a smaller one. Well, 2 times what equals 12? Well, 2 times 6 equals 12. 4 times what equals 12? 4 times 3 equals 12. So the smaller mass has the bigger acceleration. The bigger mass has a smaller acceleration if the forces are the same. Pretty cool, right? Pretty cool. All right, so looking at this one here, these are free body diagrams. Looking at this, let me get my, what does this do? That's a highlighter. Woo, won't need all that. All right, so 25 Newton force. So if we think about it like north, south, east, west, all right, we got 25 Newton force east, 25 Newton force west. They are equal. This is a balanced force, so there is no movement. Well, down here, right, that's not always the case. So we got 45 newtons north, 45 newtons south. These cancel, okay? So there's no movement up or down. And you got 15 newtons north, 45 newtons, or not north, 15 newtons east, 45 newtons west. These are going to cancel out some, and we did a little demonstration in class the other day about that. So you're not going to get the full 45 newtons force going on. You got 15 newtons pulling back. So just like we did in class with the chair, what you will see is the net force. The net force is like the sum of all forces. So these two cancel out. We're going to do 45 minus 15 because that's the opposing force. This is going to give us an answer of 30 newtons. So our net force, N-E-T, is 30 newtons west. All right, so looking over here, again, our upward force is equal to our downward force. These cancel out. These are unequal, right? This side is larger over here. So my net force, I'm going to subtract 5. My net force is 3.5, like northwest, Newton's northwest. Now, I don't know how to clear this off. I'm going to hit Control Z a bunch of times. That ain't working. Eraser. So, let's think about some things. What if I wanted you to give me more? Right? All right, good to go. So, oh, it came back. Wow, that's crap. Anyway, let's say I wanted to know what is the acceleration of the box, right? What is the acceleration? Well, here the acceleration is 0 because they're balanced. There's no movement. Well, down here, okay, so I got a 30 Newton net force. I got a mass. So this is my mass. This is my force. So I can use this to plug into F equals ma. So to find the acceleration of this force diagram, I would take my force. I'm going to solve this up here, okay? So I take my force. My force is 30 newtons. I'm going to take my mass, which is 3, and my acceleration is a. So this is multiplication. We'll do the opposite of that. We'll divide by 3 kilograms. Divide by 3 kilograms. Okay, so 30 divided by 3 is 10 newtons over kilogram equals acceleration. Now, this is not our unit. Okay, so looking at this, what we need to do, if I can get something to work.
Mr. McFarland, can you come to the front office, please?
1 Newton equals 1 kilogram meter second squared. So we're going to replace that for our Newton. So our answer is 10 kilograms per meter second squared, right? Over, bring this down, kilogram. All right, kilogram cancels out. Our unit's meter second squared, so our answer is 10 meters second squared. If that math is confusing, it was kind of quick, it was kind of sloppy, it wasn't very pretty. You can watch the math video, the next hard science video on force. But what I wanted to get across to you right there with this was just that if you're asked a question about this, you have a mass, you have a force, that's all you need. You need 2 of the 3. I'm never going to get used to this webcam thing. Like I hold it up in front of me, like you see one finger, I'm trying to hold up 2. Everything's backwards. I'm trying to move to the left. Everything's going to the right. That's science too. We ain't going into that right now. All right. Again, if you need help with the math part, the next video on force is solely on math. I tried to go as conceptual as I could with the F equals ma on this one. Let me know if you have any questions. I'll get on it.